Okay, so in this video we are going to solve a problem of a planetary gear system, and this is the system that is given to us. This outer gear is the ring gear, the inner gear is the sun gear, and the intermediate one is the planetary gear. It is given that the ring gear is rotating with an angular speed of omega-2, it's a constant angular speed. The sun gear is rotating with an angular speed of omega-1. The radius of the sun gear is r1, the radius of the ring gear is r2. So accordingly you can find the radius of the planetary gear, which we have named r3, but it can be expressed in terms of r1 and r2. At a given instant, we note that the point of contact between the sun and the planetary gear is P, and the point of contact between the planetary gear and the ring gear is at Q. The gears are obviously meshed, and so you can consider that these are disks that are rolling without slipping on each other. And we want to determine the velocity of a point C, which at a given instant is at an angle theta from the line AB. Okay, and to express these solutions we are going to use these unit vectors. So ER is in the direction of A to B, that is A, P, B, Q extended gives the direction ER. EF is perpendicular to that, and ER cross EF is EZ. So EZ is perpendicular to the surface of this page. So our goal is to determine the velocity and acceleration of C. And so C is an arbitrary point, and that point is at an instant making an angle theta. Of course, that theta angle is changing with rotation. So we are interested in finding the velocities and the velocity and the acceleration of the point C at the given instant. Now this is a nice example where there are multiple rigid bodies that are involved, and so the ideas of calculating velocities and accelerations using the relative velocity acceleration expressions in the context of rigid bodies is good here, and so we can use this as a problem to demonstrate some of those. And what we are going to do is we are going to solve the velocity and acceleration using one set of rotating frames, and then I may post another solution with a different rotating frame. So let's start with the first approach. So the approach that we are going to take to solve this problem is one where we are going to consider the rotating reference frame is fixed to this planetary gear. So rotating reference frame fixed to planetary gear. Okay, and so we deliberately make this note because we want to also show the we want to distinguish between the reference frame, okay, and this coordinate triad. Okay, this coordinate triad does not necessarily mean that we need to consider this as the rotating reference frame. See here, the way this triad is defined is that this triad is going to rotate with AB, with the line AB. Okay, so that is how the triad has been defined. Okay, we want to distinguish that choosing a particular triad and choosing a particular frame of reference are two different things. Okay, we are going to work with this triad to express all our vectors, but our rotating reference frame is going to be a reference frame that is fixed to this planetary gear. So that distinction will also be demonstrated through this particular approach that we are taking. So in any case, we are directly going to jump to this the velocity. So velocity Vc is going to be equal to, so we are going to use a reference point to express the velocity equation of c. And so in a rigid body, you can take any 2 points and express the velocity of one with respect to other. We just need to be a bit judicious of the choice of the point, because that can help us in calculations. So here I'm going to start by saying that Vc is equal to Vb, a clear choice because B is the center of that gear, plus omega cross rho c with respect to B. If you recall, in the relative velocity equation there is a rho dot r that is also added, but that term is not going to be applicable here because the rotating reference frame is fixed to the disk. And when the reference frame is fixed to the rigid body and both the points are on that same rigid body, then the relative velocity in the rotating frame it degenerates to 0. So we make a note that rho dot r is equal to rho double dot r is equal to 0 in this case since C and B are on the same rigid body and rotating frame is fixed to it. So the rotating frame is fixed to that rigid body and the points B and C are on the same rigid body, hence we don't have that third term in the relative velocity. Furthermore, we note that omega is equal to the angular velocity of planetary gear. That is, of the rigid body that B and C are part of. So in order to proceed with this, what we need to do is find the velocity of B. So we want to find the velocity of this point. We also have to find the angular velocity of the planetary gear. So these are two things that we need to determine. So in order to determine the velocities or the angular velocity first, what we will do is we will note that the point P is the point of contact between the sun gear and the planetary gear, and so because there is rolling without slipping at this point, then the velocity of P is the same whether you consider P to be a part of the planetary gear or if you consider P to be a part of the sun gear. Okay, in other words, if we can express the velocity of the point P as part of the sun gear, then that velocity will be the same as the velocity of this planetary gear at the point P, because they are rolling without slipping. So we can then say that, and you can see here that the velocity of the point P, if you consider the sun gear, is basically in the direction of E phi. Okay, so let me just, is in the direction of E phi, and it is, the magnitude is omega 1 r1. Now note that the same observation can also be made for the point Q. The point Q is the point where the planet and the ring gear are meshed and they are rolling without slipping. So at this point, both the planet as well as the ring gear will have the same common velocity. And that velocity, again, as you can see from the geometry, we don't need to do any calculation. From the geometry we can see that that velocity is going to be given by omega 2 r2. Okay, so omega 2 r2 is the velocity at the point Q of the planet, and omega 1 r1 is the velocity of the point P on the planet. So therefore Vp is equal to omega 1 r1, and it's in the direction E phi, and Vq is equal to omega 2 r2, again in the direction E phi. Right? Now, since P and Q are also points on the same planetary gear, so since P and Q are points on the planetary gear, therefore we can say that Vq is equal to Vp plus omega cross rho Q with respect to P. The same equation that we wrote between C and B can now be written between Q and P. Q and P are these 2 points because these 2 points are again on the same planetary gear. So we proceed with this calculation. So we have therefore omega 2 r2 E phi is equal to omega 1 r1 E phi plus now this omega is the angular velocity of the planetary gear. We have named the planetary gear D3. We have named the sun gear D2, and if there was a need we could name the ring gear as D2. So the sun is D1, the ring is D2, and the planetary gear is D3. Now we are interested to find the net angular velocity of the planetary gear. So we are going to call it omega D3, and since all the motion is taking place on this plane, the angular velocities are perpendicular, and so their direction is in the z direction. So we are going to say that this is in the EZ direction. Now this one can be positive or negative depending, but we know that the unit vector is going to be in the z direction, so perpendicular to the page. And this cross rho q with respect to p. Now rho q with respect to p is nothing but we have given the radius of the planetary gear as r3. So it is going to be q with respect to p is going to be with a magnitude of 2r3, and this is going to be in the direction er. Okay, now we make a note here also that you can see that 2r3 is equal to r2 minus r1. Right, so r3, although it is we have given a variable name for this, but really the radius of the planetary gear can be determined from the radius of the sun gear and the radius of the ring gear, and that's the relation. So so in the next step we carry out this cross product, and we make a note based on this set of unit vectors that ER cross EZ is E phi. So ER cross EZ, ER cross E phi is equal to EZ. and so this is the sequence in which we will carry out the cross products. So the right hand side of this equation then is omega 1 r1 e phi plus 2 r3 omega d3, and Ez cross Er is going to be E phi. So you can see that in this equation all the entries have the same unit vectors. So therefore we will have one equation from here, and that is 2r3 omega d3 is equal to omega 2 r2 minus omega 1 r1, which gives us omega d3, which is the angular velocity of the planetary gear, is equal to omega 2 r2 minus omega 1 r1 divided by 2r3, and we know that 2r3 is equal to r2 minus r1, so we have omega 2 r2 minus omega 1 r1 divided by r2 minus r1. Okay, so we have the angular velocity of the planetary gear. So it is this angular velocity that we were trying to find out, the net angular velocity of the planetary gear, and that is something that we have calculated. So in terms of this original equation which we started with, in order to find Vc, we find that we now have omega. Rho c with respect to b is quite simple because it's just this vector going from b towards c, so that's very simple. Now what we need to find out is the velocity Vb, so let's find that out. So note that we can, because B and P are on the same rigid body, we can write that Vb is equal to Vp plus omega cross rho B with respect to P. Again, since B and P can be considered on the same rigid body, whereby we have to consider omega to be the net angular velocity of the planetary gear. Now we know Vp. Vp is omega 1 r1 and it's in the E phi direction. And we know omega, we have the expression for omega. Well, over here we'll just represent it as omega d3 Ez cross b with respect to p. So the vector b with respect to p, you can see, is r3 in the er direction. So you have omega 1 r1 E phi plus r3 omega d3, and Ez cross er is E phi. Okay, so therefore we have the expression for Vb. So Vb is equal to omega 1 r1 plus omega d3 r3, and it's in the E phi direction. And we can simplify this expression. We'll have omega 1 r1 plus, now omega d3 was omega 2 r2 minus omega 1 r1 divided by r2 minus r1. This was calculated, you will see in this previous part, and from here you can also note that r3 is equal to r2 minus r1 divided by 2. So you have r2 minus r1 divided by 2. So these two cancel, and this is in the direction E phi. And so what we have is, we have 2 omega 1 r1 plus omega 2 r2 minus omega 1 r1. So you essentially have half of omega 1 r1 plus omega 2 r2 in the e phi direction to be the velocity of the point B. Alright, so now going back to this original equation, you see we have now calculated what VB is. We have determined this, we have determined omega. Rho C with respect to B is quite simple. It's basically just this vector going from B to C. So now we are ready to actually calculate VC. So let us formulate it. Okay, so VC is now going to be equal to VB, which we will put the appropriate expression for this vector shortly, omega cross rho C with respect to B, which is, let's put VB first, it is half of omega 1 R1 plus omega 2 R2 in the E phi direction, plus omega is omega d3 Ez cross rho C with respect to B. Now let's go back to this diagram. Note that C with respect to B is the vector going from B towards C. So this is a distance r3, and r3 cosine theta is the component in the ER direction, r3 sine theta is the component in the E phi direction. So r3 cosine theta ER plus r3 sine theta E phi. So r3 cosine theta ER, r3 sine theta E phi. So that's the vector expression. So next we just simplify this equation. So we have VC is therefore equal to half of omega 1 R1 plus omega 2 R2 E phi plus, actually then we have EZ cross ER, and let me just see, EZ cross ER gives E phi. So then we have plus omega d3 r3 cosine theta E phi minus omega d3 r3 sine theta ER. And the reason we have this minus is because if you go to the cross product sequence, you will see that Z cross phi gives negative ER. So we now have the expression, we have half of omega 1 R1 plus omega 2 R2 plus omega d3 R3. Now if you recall, omega d3 is it's actually written here, omega 2 R2 minus omega 1 R1 divided by R2 minus R1, and R3 is R2 minus R1 divided by 2. So we have basically plus half omega 2 R2 minus omega 1 R1 cosine theta E phi. Okay, half of omega 2 r2 minus omega 1 r1 sine theta er. So that's the so that's the velocity of the point C, right? So that's the first part. Now in the second part we want to determine the acceleration of the point C, and we are going to proceed with the same rotating reference frame, but now we are going to move on to the acceleration equation. So we are going to again express AC as a function of AB, or relative to AB. So AC is equal to AB plus, let's write the full 5-term expression, and then we will remove the terms that are not relevant. Omega dot cross rho C with respect to B plus omega cross rho C with respect to B plus 2 omega cross rho dot R plus rho double dot R. So this is the overall 5-term expression. If you were to write the overall expression, this is what you have. And we right away note that this is 0 and this is also 0, and that is because the points C and B are located on the same rigid body, and the angular velocity that is being considered, or rather the rotating reference frame that is considered, is a reference frame that is fixed on the rigid body itself. That is, omega is the net angular velocity of the rigid body itself. So omega is omega d3. Now if you go back for a second to the omega d3 expression, you will see that since we are given omega 1 and omega 2 are constant angular velocities, omega d3 is also a constant, because r1 and r2 are essentially constant parameters, and omega 1 and omega 2 are not changing. So omega d3 is a constant. So essentially omega dot, which is omega d3 dot, is going to be equal to 0. So hence, of this 5-term expression, already 3 of the terms have dropped out. Another simplifying step that we can make is a step that is valid when we are dealing with a planar problem. Now, in a planar problem where all the motions are happening in a plane, so the angular velocities are just perpendicular to the plane, in those problems, this omega cross rho, this simplifies. So it simplifies to the following. The first term here remains the same. Then we have this guy reduces to negative times a negative the angular velocity, magnitude of the angular velocity square, times the vector rho c with respect to b. Essentially, when the motion is taking place on a plane and the angular velocity is perpendicular to the plane, you can show that this vector triple product is completely in the direction of rho c with respect to b. Okay. In fact, it's just the opposite because of the negative sign. So it's just exactly opposite to this vector rho c with respect to b. And if you just verify this, but by just going to the basics of cross products, you will be able to realize this very quickly. The angular velocities, the way they show up in the final expression is that it shows up as the square of the magnitude of the angular velocity. So this observation actually simplifies this triple product for problems that are involved or that involve motion on a flat plane. Okay, and so that simplifies the calculations. So essentially you have AB minus, this is omega d3 squared, so omega 2 r2 minus omega 1 r1 divided by r2 minus r1 whole square times rho c with respect to b, and that vector is already known. You have seen the rho c with respect to b vector written over here, so I'm just going to rewrite that r3 cosine theta er plus r3 sine theta e phi. Okay, that is good. Alright, now the next step is going to be to find AB, the acceleration of the point B. Now let's consider the figure and let's try to understand how the point B is moving. Now this is a step where quick observations can help you reduce the volume of calculations that you do in solving a problem. Now you can find the acceleration of B using all these relative velocity equations and so on, but the acceleration of B is going to be simplified if you basically note that the point B is going around the point A in a circle, right? And so the acceleration of the point B is just going to be inwards. It could have a tangential acceleration if this planetary gear was accelerating or decelerating, but that's not the case because all the angular velocities are constant. So you can imagine we can draw an alternate diagram to represent this scenario. So let's say this is the ring gear. Here is the point A, here is, let's say, the point B. So B is actually going in just a circular path around the point A, isn't it? And we have also determined that the velocity of the point B is in the E phi direction. If you just look at the previous part, this is the velocity of the point B. It is in the E phi direction, and VB is nothing but half of omega 1 r1 plus omega 2 r2 E phi. So the point B is essentially traversing a circle around the point A at a constant rate. So think about the particle B. The particle B is going around the point A with a constant speed of this VB. So what's its acceleration going to be? Because it's a constant velocity, it does not have any tangential acceleration. So the only acceleration that it has is the radial acceleration, and that radial acceleration is going to be in the direction of negative ER. So we can then say, and then the acceleration magnitude is going to be the velocity squared divided by the radius of curvature, and this is a circle, so the radius of curvature is this distance from A to B. So essentially acceleration of B is equal to half of omega 1 r1 plus omega 2 r2 whole thing squared, okay, divided by, so I'm doing times 1 divided by the radius or the distance from A to B. Now if you go back to the diagram here, you see the distance of A to B is r1 plus r3. Okay, so this is v squared divided by r, and the acceleration is in the negative ER direction. So I'm going to put a negative ER here. So it's a centripetal acceleration always directed towards the center of its circle, which is at A. Now note that R1 plus R3 is equal to R1 plus R2 minus R1 divided by 2, which is equal to R1 plus R2 divided by 2. Okay, so therefore acceleration of B is equal to this term divided by R1 plus R2 divided by 2. So you are going to get a half times omega 1 R1 plus omega 2 R2 squared times 1 over R1 plus R2 with a negative sign, and this is in ER. So let me just write it in a little bit more compact way. It is negative of omega 1 R1 plus omega 2 R2 whole square divided by 2 times R1 plus R2 ER. So that's the acceleration AB. Alright, so now it's just a matter of integrating these results. So let me just put up the expression that we had for the acceleration. So this is the expression for AC that we started with. So we note that AC is equal to AB, which we have just found out. So AB is over here. Okay, AC is equal to AB plus this term. Okay, so we are going to complete this algebra. So let me just put everything together. So we'll say therefore AC is equal to minus omega 1 R1 plus omega 2 R2 whole squared over 2 R1 plus R2 ER minus omega 2 R2 minus omega 1 R1 whole squared divided by, now here you'd have R2 minus R1 squared, but we know that R3 is equal to R2 minus R1 divided by 2, and there are two R3s here. So we can factor out this R3. So we will have a 2 times R2 minus R1 showing up, and then this would be multiplied by cosine theta ER plus sine theta E phi. Yeah. So then in the last step, what we can do is we can just put together the terms that have ER in them. So we'll take this negative sign as a common factor. Omega 1 R1 plus omega 2 R2 square divided by 2 R1 plus R2 plus omega 2 R2 minus omega 1 R1 square 2 R2 minus R1 cosine theta multiplied by ER minus omega 2 R2 minus omega 1 R1 whole squared divided by 2 times R2 minus R1. Whole thing gets multiplied by sine theta e phi. And so that is our acceleration of the point C. So that is what I wanted to discuss in this video. Essentially, this is a video where we looked at the kinematics of a planetary gear system. This is very common in mechanical engineering. Many practical devices such as transmissions or other devices use planetary gears, and so this problem is quite relevant to mechanisms and machines. It's a very rich problem in the sense that this is a multi-rigid body problem with different rotating parts, and good understanding of kinematics, rigid body kinematics and dynamics helps us solve problems like this with relative ease. Here the specific goal of this problem was to find the velocity and acceleration of the point C, which is definitely a very relevant problem. However, the build-up to these velocity and acceleration expressions were also very important components in analyzing a planetary gear, because in the build-up what we did is we found out, for example, the angular velocity of the planetary gear. We also found out the angular velocity with which B turns about the point A. So at what angular velocity does the planet go around the sun, and what is the angular velocity of the planetary gear itself. So we found those out, and so those calculations are also very important in addition to the requirements of this problem. So we'll end here, and I'll try to solve this problem using another rotating reference frame, and try to show how we can choose different rotating reference frames, but we will, if the analysis is correct, then we end up with the same solution. So that we will do going forward. So thank you.